We have today a resistor and a capacitor and an inductor all in series with an oscillating voltage source. And just like last time, I have the question written in the description just to save some room up here on the screen. So we have an alternating voltage source denoted by that symbol in series with a resistor, a capacitor, and an inductor. And our voltage, our maximum voltage, we'll call that V sub 0 or V naught, is equal to 240 volts. And our resistor has a resistance equal to 100 ohms. And our capacitor has a capacitance of 0.1 microfarads. And finally, our inductor, which has a inductance of 0.3 henries. And the first thing to note about this is that since this is not a series circuit, it's a parallel circuit, and that means that the voltage across each element will be the same as that of the voltage caused by the source. Whereas in a series circuit, the voltage will vary throughout each element. And of course, because this is a parallel circuit, the current will be what differs throughout each element. So the current through the resistor won't be the same as the current going through the inductor. And so the first part of this problem asks us, what is the resonance angular frequency? So we should ask ourselves, what is resonance angular frequency anyway? But it's actually a better idea to understand what resonance is in general. And resonance is basically when the current in the circuit has reached its maximum value. And so what I'm about to do is actually kind of like a mini proof of the idea. So we know that in a parallel circuit, or actually in any kind of in any situation of resonance, the voltage will always be equal to each other in any given element. So I'm going to choose the elements of the inductor and the capacitor, and I chose those for a specific reason, you'll see. And so the voltage across the inductor is going to be equal to the current across the inductor times its reactance, which is basically like the resistance. And across the capacitor is going to be the current across the capacitor times the impedance, the reactance across the reactance due to the capacitor. And since we're talking about resonance, the currents will be the same. The currents will be the same because they will be a maximum value, but they won't be maximum at the same exact time. But nonetheless, we're showing that the currents are equal to each other in terms of their maximum value. And so what we'll be left with is just the reactance of the inductor and the reactance of the capacitor, which you know from definition. The reactance due to the inductor is equal to omega times the inductance, and due to the capacitor is 1 divided by omega times the capacitance. And because we're in resonance, we're in resonance right now, our angular frequency right here will be equal to each other because they define the moment in which they define the frequency in which we're in resonance, and so they're going to be equal to each other. So we're going to put an omega naught to show that they're equal to each other. And so after some algebra, you'll realize that the omega will be equal to 1 divided by the square root of L over C. And that is equal to, by plugging in the inductance and the capacitance, is equal to 5,773.5 radians per second. And that was probably the hardest part conceptually of this whole problem. The rest of the problem is actually very straightforward. So Part B asks us, what is the maximum current through the voltage source at the resonance frequency? And so of course we know that the maximum current will occur at resonance, and also when we know that we actually know that the maximum current will occur when we can cancel out the sinusoidal function. So that's just going to be equal to the maximum voltage equal to I times the impedance of the entire circuit. And of course we know that the impedance, which is like resistance, is equal to the square root of the reactance of the capacitor minus the reactance of the inductor minus the reactance of the capacitor. Excuse me, that is supposed to be resistance. This is just supposed to be R in general, actually. This is just the resistance minus the reactance to the inductor, then of the capacitor squared. And if you draw the phasor diagram, you'll notice this is just we just got this from Pythagorean's theorem. And so as a result, you'll see that the reactance of the inductor minus the since they're equal to each other, as we showed over here on part A, they're equal to each other, so it's just going to be, that's supposed to be squared as well. And since this will go away, so we'll be left with the square root of R squared, and that's just going to be equal to R. So therefore, this is equal to I times R. So therefore, the maximum current is equal to the maximum voltage divided by the resistance, and that is equal, if you plug it in, 240 divided by 100 is 2.4 amperes. It's the maximum current through the voltage source. And part C, I'm going to squeeze it in right here because you'll see it is very similar. Part C asks us find the maximum current in the resistor at resonance. And so the maximum current through the resistor, you'll see we can use the same exact equation. The maximum voltage is equal to I times R. And so therefore, for part C, we're just going to get the same thing. 240 divided by 100, 2.4 amperes. And for part D, they ask us what is the maximum current in the inductor at resonance. And so similarly, since we're asking for a maximum current, we can do V equal to I times the resistance or the reactance due to the inductor, because we're canceling out the sinusoidal function in order to find a maximum. And of course we know that's just equal to I times omega naught, because we're at resonance, times the inductance. So the maximum current is just going to be equal to the maximum voltage divided by the resonant angular frequency divided by and multiplied by the inductance. And since we have all those values, that value should come out to be 0.139 amperes. And similarly, I'm going to squeeze in part E down here for a good reason as well, because you'll see something very similar. What is the maximum current in the branch containing the capacitor at resonance? And they say, what is the maximum current in the branch? Because obviously there's no current going through two plates with an empty space between them, which is the capacitor. We'll find that the maximum voltage is equal to I times the times the reactance due to the capacitor, which is just I divided by omega naught times the capacitance. The reactance, of course, is 1 divided by omega. See, and if you do the algebra correctly, you'll find I equal to 0.139 amperes, once again, which makes sense because we're looking for a maximum. We're looking for a maximum current, and since we're at resonance, we should find the same exact value. But they're not going to happen at the same exact time, of course. That's the key point. There's only one maximum value of current, but not at the same time. And so part F asks us to find the maximum energy stored in the inductor and the capacitor at resonance. So let's start with the easier one. We know that the energy across the capacitor is equal to 1/2 times the capacitance times the voltage across the plates squared. Since they want the maximum energy stored in it, that's only going to happen when the electric field between the plates is maximum, and that only happens when there's a maximum voltage. And so we're going to just put that V naught to show that we're going to use the maximum voltage, which they gave it to us earlier in the problem. It was stated in the question, actually. And so we have the capacitance, we have the maximum voltage, and so all of that will turn out to be 0.0029 joules. Or more appropriately, we can say 2.9 millijoules. And then they ask us, what is the maximum energy through the inductor? And that is equal to 1/2 times, we should know this already, 1/2 times the inductance times the current squared. And of course, when is the maximum energy going to occur? When we have a maximum current, which is going to be when we're in resonance. And of course, we already found that, which we found was 0.139 amps, and we plug that in and we put the inductance in of 0.3, multiply it by 1/2, we should come out with 2.9 millijoules as well. And so this problem clearly outlines this about how the values will be similar at a maximum point. They won't happen at the same exact time. For example, the maximum energy through a capacitor will not be the same when the inductor reaches its maximum value. They will reach their maximum values at different times. That is the key point about this problem, because they are in parallel and not in series. Whereas a series circuit, we'll save that for another day because it has different properties. But hopefully this problem made sense and that you learned something from it.